example calculation. And it might not be obvious what we're trying to do with this calculation, right? It says, is the following reaction spontaneous under standard conditions? And what we would need for that is to show, well, the delta S total must be greater than 0. Or another way we could look at this is the delta G, and I'm going to say delta G standard of reaction must be less than 0. And the reason why I got very specific saying standard delta G of reaction, because that's another way of saying the free energy of our system, which is our chemical reaction. Okay, so we could certainly calculate the entropy of the system of this reaction, but then we'd have to calculate the entropy of its surroundings. Instead, we can calculate the free energy of the reaction, and if it's negative, that'll tell us this reaction is spontaneous. So we need to look up all those free energy values. And this time I didn't do that preemptively, and I wanted to show you where I could find those values. Okay, so we need octane C8H18 liquid. We need O2 gas. We need CO2 gas, and we need H2O gas. And here what I have is the appendix number 4. I'll scroll to the top of it. Chemical bonds and thermodynamic data. This came from the ebook, and it's also in your regular book. And so we have to scroll down a bit to find the table that we want, which here it is. Thermodynamic properties at 25 degrees. So that's going to give me my, there it is, standard free energy. Okay. And technically, that's the standard free energy of formation, which is like the specific free energy of that static molecule. Okay. So let's start looking some things up. And we want this rightmost column, and it's in units of kilojoules per mole. So I've got to scan through, and you can see these are all listed alphabetical order. First, they're organized by elements and monoatomic ions. We don't want any of those based on the reaction we have. Next, we have polyatomic ions. We don't want any of those. And then, inorganic compounds. So our carbon dioxide gas is an inorganic compound. There it is, negative 394.4. So let's write that down for carbon dioxide. Oops, let's see. Negative 394.4, and that's kilojoules per mole. So let's keep looking stuff up. So we need H2O gas, and that should be, yep, here it is, H2O gas, negative 228.6. And there's 18 of those things. Okay, so now I need O2 gas, and that's also going to be an inorganic compound. So let's find it. Oops, I thought it would be. Let's see here. Oh, it's under elements, duh, because it's oxygen. So let's see. Yes, elements. And let's see here. We keep looking. There's nitrogen. Aha, O2 gas. What do you know? It's 0.0. And we could have said that, but I wanted you to see that directly, right? So here's N2 gas, 0.0. Neon gas, 0.0. O2 gas, 0.0. But look, O3 gas, which we know is ozone, is not 0.0. Okay, so tread lightly when looking at these values and assuming what they should be. So that's 0.0. So the last thing we need to look up is octane, and that's going to be under organic molecules, organic compounds. And I had to scroll all the way to the bottom to find this earlier. I know that this is not totally obvious to you, so we want the liquid, and it's this compound right here. This CH3, CH2, 6CH3. If we were to count up all the atoms in that formula, that would be C8H18. Okay? Because 6 times 2 is 12, plus 3 is 15, plus 3 is 18, and then we've got 1, 7, 8. So that's our octane. Okay? And you can see it's 6.4. So it should be pretty obvious right away what's going on. But if it's not, let's just think about if this reaction is spontaneous. So it's a combustion reaction, okay? And when we were talking about entropy previously, a good test of if something is spontaneous is if it's reversible. And if you imagine here, if I combust something, if I explode a bunch of octane, there's no way in hell I can reverse that. So this should, by all intents and purposes, be spontaneous. But let's calculate it all the same. Okay, so we need to sum all the products. So that's going to be 18 times negative 228.6. And then that's plus 16 times negative 394.4. So that's the sum of my products minus the sum of my reactants, which is just 2 times 6.4 plus 0 times 25, which we don't even really need to do, right? But we will just to be exact. So I can do this part in my head. 2 times 6.4 is 12.8, and that's just going to have units of kilojoules. And then now I need to add up all of these. So that's going to be 18 times 226. Oops, that was 18 times. Okay, yeah, it was stored in there. 18 times, let's try it one more time. 228.6 negative. So that's a big number. So that's negative 4,100. I'm just going to, yeah, we'll call it 114.8 kilojoules plus 16 times 394.4 negative, and that's another giant number. So negative 6310.4 kilojoules. So hopefully you can see this is all definitely going to add up to be negative, but let's just do it just to get the total value. So I'll say plus 4114.8 negative. Okay, and that equals negative 10,425.2. And then I will say minus 12.8. So this is a huge negative number. So this is negative 10,438 kilojoules. So definitely, yes, this is spontaneous because the delta G was negative. But also, again, we could have rationalized this conceptually just by knowing this is a combustion reaction, and it is exceedingly difficult to reverse a combustion reaction, meaning this is going to be spontaneous. Okay? All right, I'll see you in the next video.